All right, we're starting. Welcome to another Common Lisp study group. I'm your host, Ron Baden with Atlantic Functional Programming. Today we're going to be discussing and continuing our discussion of the series library, in particularly the continuation of the paper on the basic implementation of series in Common Lisp. For those of you who have joined us last week, I posted the links to the particular papers that we're covering. One covers actually the API reference, which I encourage most of you to actually keep kind of like at your side as you go through the series library, because there is a significant number of things that are already built into the library. And of course, keep a copy of the implementation, just so that you have an understanding of not just the design decisions, but how might you want to extend that to adopt, additional abstractions. Before we get started on actually covering what we're going to be covering today, a couple of announcements. The High Talk is going to be coming up in the couple of weeks. I think it's going to be, I'm expecting end of October is the current tentative thing. I'm going to be posting that initial announcement today after we're done with our discussion on series in the study group. Additionally, the current tentative schedule for the FP and C++ series has been postponed by a couple of weeks just due to a couple of things I noticed when I was designing some of the material for it. Once I have a more definitive plan, I will go ahead and post on the meetup page for additional announcements on that, as well as an agenda of basic topics that we'll be covering. Also, I would like to mention that Atlanta Functional Programming is looking for speakers, as usual. Folks who want to give a talk on anything FP related, choose your language of choice. You could also think about talking about design discussions and so forth. Please post either a comment or talk to me or ping me on either Discord for the Lisp Discord server or Functional Programming Slack. I'm usually available there for folks who are in the Atlanta area. Of course, you know that I tend to squat in the Functional Programming Slack channel on Tech 404. That's a specific channel on Tech 404, along with the Lisp channel there. Feel free to ping me, give me some ideas, say, hey, I want to give a talk on this particular topic, and we'll try and get you scheduled. Okay, so let's get started here. Let me just do one thing here to see if I have an adjustment. I have to, of course, share my screen with my fellow Hangout buddies. Okay. And down a little bit. Right. And pull up my notes I was writing this morning. Let's do one more thing here, which is okay. All right, let's get started. So last time we discussed the 5 restrictions that were kind of necessary in order for you to build these kinds of series expressions. To review, these are this notion of what the paper calls an optimizable sequence expression. This is something that is statically analyzable, something that does not create a control flow graph that induces a cycle. It has to be a fairly straight line computation. For folks who want to get sort of analogy, the best one that I can come up with now, it just came to me when I was reading some of this stuff again and reviewing it, was a source to sink sort of analogy, where you want to actually do a certain number of transformations. Usually, this is the transducers using the series speak, and you're taking data from this source, which is a scanner, going through these different transformations, which are the transducers, and you are going to put it into a sink, which is called a collector inside series. Additionally, of course, the procedures that are called by the sequence expressions must be a pre-order, meaning that they are expressions that that sort of imply a particular order that you can, again, related to the straight line computation, you can easily go and schedule them. You can't actually move them out of order and do certain computations in an out of order way. So again, this is all related to the first two restrictions. Also, and this is a very important one because this is related to one of the things that series was trying to kind of remove, which is the spatial overhead when you're dealing with sequence expressions that tend to create intermediate sequence representations. And the way they avoided this is by allowing each of your optimizable sequence expressions return sequences in between expressions. Internally, the series library, which itself is kind of a meta compiler that will compile your expressions into the appropriate Lisp code, it will take that and recognize that these are intermediate sequences that need to be moved, using the C++ parlance, moved as temporaries into the next stage as inputs, so you don't incur that spatial overhead. Also, and this is the final thing that we talked about, which is that the cycle, that a data flow graph, if you draw out the optimizable sequence expression in the diagram, the non-directed cycles must be an online expression. And what online was defined as last time when we looked at this is the initial element of the online input is always read, and then it is written, and then the second element of an online expression is read and then written, and so on. So each element of a given collection is, interacted with, executed, transformed one at a time. So that is the definition of online versus offline. And you can look at the details for examples inside the paper for more examples. So I won't cover them here. But one thing that I did want to cover is this one thing that the section after bringing up these five series that I didn't cover last time that I wanted to cover today. That is, these restrictions are actually, and this is actually surprising for folks who read this paper first, and again, this was published in 1989, by the way. This work was actually, and the restrictions that we saw were actually the result of a decade's worth of research. Actually, the paper explicitly says about 12 years worth of research in how to remove loops and make things more declarative. That these restrictions were kind of discovered and kind of encapsulated and codified. So that means, although we're now looking at this again, what is it now, 89, 21 years later, the work is actually about 33 years in the making. So you're looking at 1970, late 70s, where some of this stuff was kind of discovered, which is very impressive. That I think hardware finally caught up and allowed us to actually leverage some of this stuff. There's a couple things in here that I wanted to bring up, specifically, which is the approach the author suggests programmers take to adopt this kind of series style of declarative writing of their sequence transformations. And that is to write expressions without worrying about their restrictions, and then start fixing it if a constraint is actually reported. So in the Lisp world, you could do this by simply interacting with the sequence expression on the REPL, and tweak the sequence expression until it comes to something that gives you the results that you were expecting for. This way, you don't necessarily start with a sequential version of a computation and then try and refactor it. And there's a reason for this. A lot of folks, once they see a kind of executable piece of code that is working, their unit tests are passing, they tend to rely, and if it looks good enough, especially with templates or cognitive forms that most people can recognize, because familiarity of loops is recognizable for anybody looking at other programming languages. They will tend to err on the side of familiarity rather than trying to improve the kind of documentation on what exactly the computation is doing. So obviously for a new programmer, seeing, say, a reduction, even a simple reduction here in the functional programming sense, before we even start talking about series, this looks at least a little easier for folks who understand the language constructs of the language that they're using, versus saying looking at even the simple loop form, because of the fact that you have to recognize what the loop is actually doing and actually parse through the loop to actually see what ultimately the output of a given particular piece of code is going to be. So, there are other approaches to these restrictions, and the paper goes through a bunch of these, specifically some stuff from Philip Wadler on restrictions for sequence expressions, because Wadler did quite a bit of work before moving on to Haskell on listless transformers to improve the performance of certain Lisp expressions, which I encourage folks to actually go and look into and check out. But the reason I'm mentioning it here specifically is because there's still a design space with respect to the restrictions that the author himself kind of admits that he didn't go through and try or experiment with. Although he does do a comparative analysis with some of the work that Wadler did and his, because he wanted to talk about the pipelining design that he created versus what Wadler did, which is focusing on the storage problem related to keeping track of intermediate characters. So we're now at a point where we can actually start talking about, well, how exactly are series now then implemented inside inside this library? And the series library itself implements them in a closure-like fashion. There's an unoptimizable version of this in the paper that we will be going over today. But I'm just covering right now some of some points, key points that were mentioned inside section 3 of the paper. If you're looking at the paper, let me just pull up something here. Just one question, folks that are on the Hangout, can you see the Emacs screen now? Please respond.
Yes.
Sweet. Thank you. Just want to make sure. Thanks.
Yeah, I see your
all right.
with open file and let stuff.
Great. All right.
Grow, etc. And FGH sets that.
All right. So I'm going to switch over to a different file. I'm going to keep this open just so that we can actually separate what we're doing in terms of the basic usage from what a basic implementation of this library might look like. For folks who are looking at this, I already did update the README file in the AFP workshop GitHub repository. So once we're done with this, I'll go and check that in and push it. And folks who are watching this video on YouTube Live, I will post the actual the GitHub URL in the description, so that for folks who want to go and take a look at it, they may certainly do so. And then after today, of course, you'll have today's discussions. And folks watching the stream, if you hit refresh, the GitHub repository is in the URL. All right. So let's start with what exactly is a series data type. Again, series, the name was brought up because of the fact that sequences have been kind of built into a lot of languages and goes by many names, and series is dealing with also not just that data type, but also the operations related to the kind of transformations that you want to do, and the design space, the way they expect you to work with sequences. You could think of the idea of the series data type, at least its nomenclature, coming from the world of, just again, mathematics, and which a lot of terminology from functional programming kind of adopted. Because in series expressions in mathematics, they take a sequence, a known sequence, which is defined by a function, and they specify in the summation of the series, which is usually not just a summation necessarily. It could either be the sigma, which is a summation, or a pi, which is the product operation of the potential function that you're dealing with. But in both cases, what it's doing is it's doing some sort of reduction from some sort of source after a series of transformations are being done, where the transformations are defined in the body of the series expression. A simple idea of this, just to kind of illustrate this for folks who don't remember their math, is, and I'm going to be writing this in LaTeX here, but let's just say that you had the expression x equals 1 to infinity, and you're just trying to sum up, or let's say 100 of the expression x. This actually is just doing nothing more than summing the first 100 integers, which we've already seen in last episode on how we might go around and actually designing that. So what does series build then, the data type build on top of these existing sequences then? If you just what you just said, that there's a sequence type built into a series, couldn't we just mimic this in some ways using either compiler tricks or just implementing library operations that take in sequences and return sequences? Where the magic lies is actually in the compiler extension, and that's where it takes a series expression and actually goes and converts it into the appropriate either loop variant or something even easier that could generate the same amount of code. To start with, let's talk about how different languages implement sequences, and then we can get started with series. So most people are aware of this, but just to reiterate, technically speaking, sequences can be implemented as either vectors or which are contiguous blocks as well, or array lists if you're going from the Java land. They could be linked lists as well, technically, because of the fact that you can still iterate through each of those one at a time. There are other such data structures that you could implement in an iterative fashion. One idea is even a simple map, which it can be treated as a list of pairs, or an associative array, which is also a list of pairs. A lot of those can be implemented as a way as being a sequence of those particular operations. What series adds on top of this is some additional kind of restrictions or additional features, if you will. Informally, or at least with respect to common Lisp, series behind the scenes are like vectors. So think of them like dynamic arrays. But they can be unbounded and linked. So that means that series can be infinite. You can have a series that could generate an infinite number of integers. Of course, when you're designing your series expressions, at some point you're going to have to provide some sort of terminating condition, otherwise you have an infinite loop. The discussion about that I want to bring up on this section 3, which kind of further goes down this rabbit hole, is based on this given data structure, okay, that we can simply, say, and I'm just saying this for illustrating this for a simple case, this is our main series. Obviously, this won't be a main series because of the fact that this is still going to be somewhat of a fixed array right now. But you could think of this being able to be adjustable, essentially. So you could say and I'm just making a single-dimensional series right now. We're not even talking about multi-dimensional series because the library itself doesn't support that. The basic idea is that internally a series is going to be just this kind of vector. But on top of that is actually what makes things a little bit interesting. And that is the 3 abstractions that were built on top of the series library. And that is scanners, transducers, and collectors. So, as I mentioned before, and as the series documentation mentions, scanners are your essentially the data structure or the abstraction that will produce elements in a series. A scanner actually has a very formal mathematical definition that's actually mentioned in the paper that I'll just briefly mention here because I don't have all the nice LaTeX symbols in my Emacs buffer. But the idea is a scanner actually has 3 parts, okay, when you're constructing a scanner object, okay? One is an initial value, okay? We need to know where does the production of these series, actually the internal sequence, where is it actually starting from, okay? And you're going to see this in a lot of the transducers as well as the collectors as well. There's some sort of initial condition. Then you have 2 functions, okay? One function is your step function, okay? The second function, so this is let's call this f, is your step function. And this is essentially defining how the next element is computed. And then, of course, you need a P, which is just a predicate that determines how do you terminate. What is the ending condition for this particular series? And again, this is nothing more than saying, okay, are we done yet? For infinite sequences, obviously, we'll never be done, so this will always be false. For which means your collector has to determine how to actually terminate the actual process. But for finite series, which is, and a simple example is like scan file. Scan file has a finite condition. Are we at the end of the file? That's your predicate. Your predicate will actually determine that. And this, let me just go ahead and let me just write this down. Given these three arguments, if you will, right, scanning can be defined as nothing more than, and I won't use mathematical notation here, but you can think of this if you're looking at this in an algol-like way or a C-like way, it has nothing more than being a function. This is just pseudocode here. If P of Z, okay, so that means are we at the end? Then return. Otherwise, you can actually say return nil, or otherwise you are just concatenating, and the operation that they use for concatenation is actually two pipes, which I know for folks that are looking at this are going to be like, that's a logical OR, and it's not a logical OR in this case. I could, use concat here, Z with the rest of the series that which is calling, scanning, on, and then you define your series as being the next element as being the initial value, and then your predicate. Okay, that's all series a scanner is. Okay, a scanner is literally just a recursive function that says, hey, can I? Are we at the end yet? No. Okay, let's tack on another guy to the scanning. Very simple. No, magic about it, but it's a very clear recursive definition that in hindsight is always 20/20, and so looking at this, you'll be like, well, that looks obvious. Why are you bringing this up, right? But at the time, this recursive definition wasn't really thought to be efficient, or they're like, oh, that's an aspirational goal, but that's something that we that may not be efficient now given the hardware that we have. So we're just going to go and do this the other way. Now, when I read this, I also found out that apparently the actual initial implementation of series has not just the 4 scanners that I mentioned, and I illustrated in past episodes, but according to this, the Lisp implementation supports 15 different scanners. So my suggestion to folks that are exploring the series library, I have not gone through the API documentation with a fine-tooth comb, as to know when different scanners are useful for which. And that might be a good topic for a future episode of this when we get done with the discussion of the implementation. But folks who want to start with using series today, my suggestion is, before you think that you need to create a new scanner and try to adhere to some of the design points that I'm bringing up in this presentation on the implementation of series, please go into the documentation and see if there's already a scanner that suits your needs, because that will save you a lot of time. Any questions on this? Just take a look here. Okay. All right. Let's talk about the opposite end. We're not going to be talking about transducers just yet. Okay. We're going to be talking about collectors now. which I like. I use the term sinks when I look at collectors, just because yeah, they're collecting stuff, but really what you're doing is you're writing data into something. Okay, and source of sinks are something that I'm very familiar with. Um, collectors have a very similar recursive definition uh, that that we saw with scanning. The difference between collection and scanning is just one argument. Z, we still has our. Sorry, I just noticed something here because I'm using X. I may as well use X. The paper uses Z quite a bit, but I mentioned it as X. Okay. So we have our first initial argument with collectors. And this here is the initial value for a collector is usually the identity of the function upon which you are reducing the collector with. Okay, and that technical explanation can be boiled down to a very simple sentence. Z represents whatever your function that you're passing into the collector. If you pass in any value and you apply the function f to that value in Z, you'll get the original value. So basically, usually left identity is what they call this of next argument. So f of xz is equal to x. That's basically what that means. When you see left identity, if you see anything related to identity operators or identity functions in any sort of literature on functional programming, all that means is if you apply the identity value, regardless of which operation that you end up using, it depends on the operation though, of course. You can't just say that it's, you can use the same identity value on a different operation. Each operation or each function has its own identity value. But if you use that identity value with that given operation on any argument, additional argument, you'll get back the same argument. That's what identity means, and that's what this left identity is. Now, left identity versus right identity, that's another topic. Basically, series was designed to essentially define collection as left fold if you're coming in from other languages, or a left reduce. It's not a right reduce. So if you think about reduction in terms of languages like, say, OCaml or F#, I don't believe Common Lisp has a right reduce. I could be wrong, folks. If there's a library out there that has a right reduce, please correct me. But as far as I can tell, Common Lisp doesn't have that. The left reduce operation basically does what collectors are doing in series, and that is they take an initial value, they pass in the thing, and then they apply that left to right. So the first argument is taken in from the left side, and then the second argument from the left side, and so forth. So that's what that means when they say that they're choosing the left identity instead of the right identity. Because depending upon the associativity and community, some operations are not commutative or associative. The commutativity determines whether or not the same value can be both left and right identities. But I can't. That's a longer discussion on just the identity operators and reduction itself. The second argument for f is not a unary function, but a binary function that takes in the initial value that we just passed in, as well as the current application of that, the current value of the sequence that we're reducing. Okay, and that's a very important thing to realize, because when you're debugging these expressions, you are going to often encounter the situation where you want to look at intermediate results, and knowing how this binary function is being applied will allow you to create intermediate results, or a function that generates intermediate results. Finally, the third argument of this is the series that we're applying the collection on. Now, this requires a little comment. The series that we're applying the collection on doesn't necessarily mean that you're just straight up attaching the source to the collectors, because then you're not doing anything. The series could be the result of sorry to overuse the word, a series of transformations, a bunch of transducers applied on top of a given scanner that we initialized. This has the same kind of recursive definition that the scanner has. Specifically, what this is doing is it defines series as being if empty, if the if the series is empty, that means, or we're at the end of the series, then we're just returning z as being the value. Otherwise, we return the collection of the function applied to the initial value, which we call s naught here, of course, and then the rest of the function, which let's call s prime. S prime in the paper is s complement. That is, it's an s with a line over it. Since I don't have that, I'm using s prime as being the rest of the list. Okay, s with the line over it in the paper explicitly refers to the tail of the series that you are actually returning, or using the common Lisp nomenclature, the critter of the actual series that we're actually applying to. Given this example, there is one simple application that they obviously showed here. Let's say that we are applying this on an anonymous function, which I wish I had the lambda stuff built in. Let's say that it's slash lambda xy dot x plus y, and we're applying this on the series data type 1, 2, 3. Obviously, for folks who are looking at lambda notation, they know that this anonymous function is just a summation operation that's summing 1, 2, and 3, and we'll get the 6 as being our final value. This example just illustrates an application, the usage of this API, if we go ahead and define it this way. But the key thing to note is and the key thing to probably get away with this particular section is that transducer scanners and collections are all based on a very simple recursive definition. Now, they have some other examples in this section that I encourage you all to read, and they're all very, very simple. Again, recursive definitions for applying particular operations that you would think about in a functional way on top of a series of on top of a sequence of series. But I will let you guys go through that specific thing. The one thing I will mention is that the The one that they defined for mapping, which maps function f over some series, producing a series of results, that's a little different than the map function or map car in Common Lisp, specifically because map car in Common Lisp returns individual elements of the actual sequence instead of the the entire sequence itself. Now, I don't know if one of the other map functions might be the same. The One of the map functions might be similar to this function definition. If you guys find that, it'll be very, very interesting. Let me know. It might be like mapcan or some other version that will take in a sequence of collections and then apply them and give you a sequence of collections as a set of results, but I don't know. Okay, let me just see one thing. So it seems to talk on. Oh, very nice comment from one of our things. Yes, so the comment was related to a different a talk on identity that this person found, and that is an identity value and the left-right identity reduction does need to be understood in algebras, but not functions or data types. Yes, that's a very good comment, and very good observation that presentation brought up. If you can provide me the link on that, I would post that in the description for additional resources for folks to understand some of this stuff. So one more thing that I wanted to take a look at was, okay, so section 3 goes through a lot of these different recursive definitions, as I mentioned earlier, and they talk about mapping, they talk about something called truncating, which cuts off a series based on a particular predicate and allows you to terminate a particular series once a particular predicate is satisfied. And the example that they give you is obviously is one where, if you have a predicate that checks for cutting off a sequence when it hits the first negative element, you could see how those intermediate representation is there. He also defines two other things. One is mingling, which combines two series into one under the control of a comparison predicate, as well as choosing, which is something that we've seen before. That's choosif. This is the definition of choosif that's inside the library, and this will allow you to pick or select elements of a series that satisfy a particular predicate. And these different operations that I'm mentioning, mapping, truncating, mingling, choosing, all of these fall under the category of transducers, which is their definition, the paper's definition of something that transforms a sequence into another sequence. Okay. Now, folks coming in from the closure world, all right, and I'm saying closure, not closure, as in the lambda closure. The closurists would say, well, how is this any different from closure transducers? I don't know. I've never actually used transducers in closure. I have to go and do a comparative analysis in them, and as soon as I get a better understanding of them, I will, provide an update for folks on this. But right now, my familiarity with closure and transducers and closure is very, very limited. Now, there's a couple of other higher order transducers that I wanted us to cover before we actually get started on the implementation specifics. One of them is this idea called spreading in this paper. I wanted to see if I could at least write out the pseudocode in based on their recursive definition, just to get an understanding. So let me define what spreading is first. Spreading takes a series of non-negative integers and a series of values, and then its output is a series containing the elements of the actual series itself. Yep. So the first argument is non-negative integers, the second argument is a series of values, and the third argument is some elements that follow that subset. So in the output, what happens is the elements of the series are spread out by interspersing them with copies of Z. So if the ith element of R is n, then the ith element of S is okay. So what this does is, and I'll show you what the operation is doing, is the usage is probably will illustrate what this operation is doing. So spreading takes example of a transducer. Spreading takes a series of indices, a series of numbers, the actual original series, and some sort of filler value. And what it does is it returns a series itself with n copies of a given number Z until the first element in the collection is encountered. So let me show you what its use is like. I don't know in what case you would actually use this, but it sounds like a very interesting operator to have. So let's say that you have a function that takes in two vectors, okay, and some filler value 0. What this is saying is it says create a vector S prime, okay, where before -7 I have 3 copies of 0, and before -1 I have 1 copy of 0. So this is what the output of that function is. And the actual recursive definition of this guy is very, very simple. It does, if we do, so again, it's spreading, and I'm just going to use R and S here for the series and the number of copies, respectively, and some filler Z. And what I do is if either empty R or empty S, then we return just, the empty list, okay? Else, if R0 equals 0, then what we do is we return essentially the initial value of the series and then apply that to the complement of the rest of the series that are available. So in the case that if they're all 0, then obviously you're going to end up just getting, this is just going to be an identity function. Otherwise, what it does is it's going to do the following. Else, we return the following. We take the series Z, and then the recursive call, which is a tail recursive call, is just R0 minus 1 concatenated to R prime. So that means what we're doing is we're modifying, this is how you would modify R when you're passing it into a function, so that, that an element of R, and then create a new R value, S and then the Z. And what this is doing is just until it hits 0, it'll just keep going. And then when it hits 0, obviously it's going to inject. This is the base case that it's going to hit, and then it will move to the next value inside of the list. Okay? This is an interesting thing that, maybe at some point when we're doing, we could go and try and implement ourselves when we get a little further. Excuse me, let me just take a little. Okay, so let's talk about the actual implementation here. I'll let you guys go through the rest of the implementation there. There's like 2 additional operations there. But let's talk about the common Lisp implementation. As I mentioned, series itself can be implemented in any programming language. So for folks that are on here that are so ambitious to take a look at this paper and say, you know what, I think I can implement this in, say, C++. You could certainly do so, and the author goes through some design discussions on how to implement that in Pascal. So I encourage you, if you're going to do that, read through the rest of the paper then, instead of doing what I did, which is kind of stop at the common Lisp implementation. Although I may just out of curiosity to go read that thing just to see how it's done in Pascal. But for the sake of today's discussion, we're going to be talking about only how series in the unoptimized sense is implemented in Common Lisp, and then we'll go from there. The optimization, the reason why I say it's going to be an unoptimized version of Common Lisp series is because, as the author mentions in the paper and as it's illustrated also in the reference manual, not to mention if you go and read the actual source code of series, series implements a preprocessor and a subsequent metacompiler has a series of macros inside of its library that will optimize the series expressions, leveraging the 5 restrictions that I just mentioned: the static analyzability, the straight line computation, etc., etc. The macro passage will take a significant amount of time to go through and understand. I won't be covering that here. The paper itself doesn't actually cover it too, because it's kind of a secondary exercise in compilers to actually go and optimize that so that you can get efficient code. So we won't be talking about that. But I do want to mention it here just so that folks who are actually watching and maybe referencing this in that later time, and they were wondering how the series library will take, say, a series defund like we have illustrated in test series there, how that gets compiled through a given application of it. All that information is in the source code itself. Okay. That's all the prerequisite material. Let's get started and write some real code. So, in Common Lisp, in unoptimized Common Lisp for series are implemented essentially as a closure. I'm pretty sure most of you figured that out, but in case you didn't, yes, it's implemented as closure. One way of actually defining this closure is having 2 parts. One is a procedural part. Specifically, this closure will have a procedural part and a data part. The procedural part is nothing more than what the author calls a generator, and for folks coming in from other languages, yes, this generator is kind of similar to those other generators, except we're not using generators like coroutines. It's not actually yielding the next value. But it is doing some sort of similar behavior in yielding because these are implemented lazily. The elements of a series are then accessed using a different generator that enumerates through the elements that have already been collected, and then uses a procedural part to compute more as they are needed. This is how it essentially memoizes predefined, pre-computed values and then moves forward. The 2-level generation scheme for anybody who's used memoization or lazy evaluation in other languages are pretty obvious. You compute things until they're needed. You don't compute the same thing twice, and then you can access all the elements if it actually terminates. So an example of this is let's say that I'm updating the code because the code is using setq in the paper. I'm just going to be using standard Common Lisp here. Let's say that we're actually going and creating the first 5 elements of the first 5 integers, right? So we create an initial condition, obviously, just like any other closure. This should not be new for folks who are looking at this. And one way of actually, of course, defining this is the list, a list that takes in 2 arguments, a lambda that generates the function, that generates the next value, okay? And what it does is it simply does the following. If x is less than 5, okay, then we obviously update x. And this is not using, by the way, we are not caching anything just yet here, all right? This is not caching anything. This is just simply doing exactly what you would normally do in the case of non-caching. But when you want, if you want to make this cache friendly, of course, you would probably make that x not into a what's it? You may keep track of, like, say, you may make x into like an empty vector, or a vector with 1 element being the first element, and then it will just go ahead and generate that. But it's not something that we're going to be illustrating here just yet. The next thing that we'd want to do is oh, wait a second. There is, I think, one thing that this particular code. Oh, got it. That's right. If obviously x is greater than 5, we'll just call the end predicate. The at end is nothing more than the predicate that says that we're returning the empty vector. So this is your basic definition of series. You just created your first dumb, unoptimized series. And we can obviously, and we'll see this later on when we add a couple of other functions. We'll be using this later on. But we're going to define a few more functions here that is our own. One is, let's say that we want to define chooseIf, okay, which is a transducer that actually goes and applies what we're doing and generates what generates based on the predicate a series that would where each element of the series satisfies that predicate. Obviously, before we could do this, we need to first do one thing, which is because remember, this is going to be in a functional way. We need to be able to create some sort of some sort of intermediate structure that's going to then be used by chooseIf to actually go in and do what it needs to do without actually incurring that spatial overhead that we're talking about. And what this function does is it just returns a generator for the different elements of the series so that you can access each element of that series in a particular way. And this guy, and I'm just going to go ahead and just write a couple of comments here, just so for folks who are just going to be reading in on this. 5. This guy, generating of the series, all it's doing is we let G be the car of the sequence, right? And then what we do is we return a closure that when you're at the empty set, what it will do is it's going to set the cutter of the SRS to being a simple block function, a block scope element that returns essentially a list that fun calls the generator on a no argument constructor that just returns a t. Okay. More. That's great. Okay. Otherwise, if it's not empty, then what we're going to be doing is we need to call the generator that the next function that we internalize, we built in. And when it's not EQ, what we do is we just car the setf as of the pitter. And this is all manipulation of the actual internal series data structure that we created, which again, as you saw, is just a closure of two things. And what we do here is we just call the predicate to say, hey, go through this again, see if what we have is actually going to work. So we now defined a generator. We're going to use this generator generator s, and now we have a generator. We're going to create another closure because again, this is all you're going to see a lot of this. This is you're in order to do lazy evaluation inside Common Lisp. You apply a function, return a function. Apply a function, return a function. This is how you do it. You'll get a thunk. You'll get a block scope value, and you'll end up not unless it gets fun called. You'll end up having a piece of stuff that hasn't generated anything yet. So again, we have this now, and this is creating the closure of actually going through and fun calling each value of the actual generator with the end action. And this is going to return potentially a value. It's going to be potentially going to be a value of the next item that we are going to be analyzing it. And of course, what we need to do here is, although the author uses this syntax, he does if fun call px return x. I think we could just simply simplify this to being when. But I will not do that for now, just so that for folks who are following along can actually go and then and once all this works, we can do some cleanup and just make sure that this is all doing this. So we defined essentially a generator. Let's just review this here. Let's get this. So we defined our data structure, which is our series data type has a closure that takes in and it implements a simple function that essentially returns the first 5 integers. And then what we've done is we've said, you know what, we're going to wrap this guy and only call this function potentially when we need to. You're going to see how this all hooks up later on. That's what this generator does. Now we've created our first transducer, which is essentially, remember, it's taking in a sequence, it's creating a sequence. So we're now creating the sequence that satisfies that given predicate. Finally, we're going to have some sort of collector because, again, the way series works, you cannot just simply take a bunch of series and then transducers and expect them to be computed. They need to go to some sort of destination in order for the compiler machinery to hook everything up and make sure that everything works. So this guy is going to take in a series, and all this is doing is, it's going to also do a generator too as well, because again, this follows our standard generation scheme. Additionally, it's going to create the initial value that we're going to have, and this way you don't have to specify the initial value to collect sum. And I think collecting or collect sum in the series library doesn't expect you to pass in the initial value. It expects the identity operator or the identity value to be built in to the actual collector itself. Now that we have these two, what we could do is we could just simply loop like we're doing before, and and the reason we're doing this loop instead of instead of using a recursive definition is merely because this will at least be somewhat optimal, not completely as optimal as generating the code ourselves using go-tos and blocks and very primitive Lisp, but it will be decent enough for us to actually go and try some stuff out. So now what we'll do is we're just going to go ahead and apply the generator on top of our ending condition, which is lambda return sum, which is just basically the way for collect sum to return something. And then what we're doing here is we're just summing up values. Okay. Let me just do one thing here, which is implementation of an example collector using the collection definition computes collection 0 x plus y yes. Okay. Actually, let me see. What is this line on? Oh, it's on line 1. Okay, let me see if I can actually move this to another line. Yes, I can. Yes. All right. So we have our transducer, we have our generator, we have our collector, we have our scanner. Let's see if all this works. So we're just going to go ahead and I'm going to go ahead and do this on the command line because otherwise I'm going to have to put a specific. I'll go ahead and do that. Collect sum, choose if, and we're just going to do odd, which will give us 1, 3, and 5, obviously, and on the first 5. Hopefully, if all works, we will get, oops, and I realize that I'm using my stuff without my earmuffs. Okay. And you can see that this is actually generating 9. So just notice what we've just done here. Okay, this is very, very beautiful, right? This here is just by using lambda Lisp closures, we've created essentially a way of creating infinite sequences. We created a way of actually being able to create intermediate infinite sequences. We created a way of yielding them and actually syncing them. And we did not do this with any sort of modifications to the compiler infrastructure. This is a very good application of the closure-oriented programming stuff that we've talked about in past episodes. And in series, adopting this and using this as part of its basis when it's doing additional optimization is really a testament to the simplicity of the design and the goals in there. So that's what I wanted to cover, and that's what I wanted to actually talk through to you today. There's, of course, other things that we can do. We can actually create series procedures on this, and I'm hoping, probably at some point when we at some point we could discuss some of the more advanced features of the series library. That's probably going to be next week. But this is what I wanted to cover today, and I think this I'm opening the door to questions on how some of this is. For folks who are interested in this, and I'm just going to show this. This is what this kind of code boils down to. Now, I had to do this in order to get this to disassemble the way I would kind of wanted it to. So and let me see if I could bring this up here. And you're looking at undefined variable. Hold on one second. Let me do it this way. Disassemble. So this is what the actual code boils down to. It's a very simple implementation. You can look at this and compare actually this to, let's say, if we go to source, test series.lisp and implement, say, series. Let's say disassemble lambda series collect some series choose if p and do series scan. Oh, right. I forgot I use in here. I can do scan. I use a scan before on this. Oops. Scan range is what I want. Yes. From 1 to 5, 5, 1. And you can see the difference between the series implementation or unoptimized implementation. By just switching over to the series implementation, we've saved close to 20 bytes. So there are a couple of instructions that we've saved, a couple of optimizations that have been found that they could do. But this alone is actually pretty impressive for an unoptimized version of series that I thought was pretty cool. But now, of course, I have not actually gone through and seen and done a comparative analysis of each instruction that's actually generated here. But when I did this the other day, I was like, huh, okay, there is a bit of a significant savings there that could be potential for a larger program. I'm going to leave it at that. Are there questions from either our live stream audience or the folks on the Hangout? Okay, well, I appreciate you all coming. Like I said, next week we'll dig into some of the more advanced stuff into the series library itself. Now that we've kind of covered the basics of this, and you can see that it's a fairly simple, very simple idea, but it really like embraces a lot of the essences of functional programming that I kind of enjoy in the Common Lisp world, the way it's defined there. Like I said, look for more announcements for our High Talk, our functional programming series in C++, as well as next week we will be discussing, folks on the Common Lisp study group, the rest of the series library itself, now that we've gone through some of the basics of how it is implemented and how we might want to eventually implement our own scanners, transducers, and collectors. So until then, thanks. I appreciate you all joining.